Welcome, rock enthusiasts! Today we're diving deep, literally and figuratively, into the wonderful world of igneous rocks. Now, I know what you're thinking. How exciting can rocks really be? Well, buckle up, because we're about to turn molten magma into pure geological gold. This isn't just about memorizing names. This is about understanding how Earth creates its most fundamental building blocks. Think of this as Earth's recipe book, and we're about to decode every delicious ingredient. So grab your metaphorical hard hat, and let's explore how magma transforms into the minerals that literally build our planet. Here's the dirty little secret geologists don't want you to know. Nature is messy. Look at these beauties. Granite, diorite, gabbro, and peridotite. They look completely different, right? But here's the kicker. There's no magical line where granite suddenly becomes diorite. It's like trying to figure out exactly when orange becomes red. Good luck with that. Nature gives us a gorgeous, continuous spectrum of chemical and mineral variations. But we humans? We love our boxes and labels. We're like that friend who color codes their closet. So we've drawn these artificial boundaries. Think of them as geological speed limits, to make sense of the chaos. It's like dividing a thermometer into hot, warm, and cold. Are those real boundaries? Nope. But they sure make fieldwork a lot easier than saying, well, this rock is kind of granite-ish, but also sort of diorite adjacent. This is the eternal battle. Genetic reality versus utilitarian classification. Nature's being artistic. We're trying to make a catalog. Spoiler alert. We're going to use that catalog anyway, because try writing a field report without rock names. All right, class. Imagine you're trying to identify a mystery rock. You've got 3 tools in your geological toolkit, and each one tells you something different. Let me introduce you to the 3 pillars of classification. Think of them as the rock identification trifecta. Pillar 1. Chemical basis. This is your lab nerd approach, super precise, super quantitative. We're talking about silica saturation here, which is just a fancy way of asking how much silicon dioxide is hanging out in this magma. It's like checking the nutritional label on your food. The downside? You need expensive lab equipment, and it tells you nothing about how the rock actually formed. It's all about the what, not the how. Pillar 2. Mineral basis. Now we're talking. This is the field geologist's bread and butter. You can actually identify rocks by looking at them. Imagine that. We distinguish between essential minerals, the main characters of our rock story, and accessory minerals, the supporting cast. This is what you'll use when you're out in the field with your trusty hand lens, trying to look smart in front of other geologists. Pillar 3. Texture and occurrence. This is where things get juicy. Texture tells us the rock's life story. Was it cooled slowly deep underground, or flash frozen on Earth's surface? It's like reading a rock's diary. Did it form under high pressure? Was it bathed in volcanic gases? This pillar reveals the drama of the rock's formation. Together, these 3 pillars give us the complete picture: chemistry, minerals, and texture, the holy trinity of petrology. Time for some magma chemistry. Don't worry, no lab coat required. Let's talk about the saturation principle, which is basically the Goldilocks story for rocks. Oversaturated magma is like that person who puts too much sugar in their coffee. there's excess stuff floating around. In this case, we've got extra silica that forms free quartz. Too much of a good thing. Saturated magma is just right. The silica is exactly enough to build feldspars, with nothing left over. Perfect balance, like a well-made recipe. Undersaturated magma is running low on silica. It's on a silica diet. So instead, we get olivine and these exotic minerals called feldspathoids, like leucite and nepheline. These are the minerals that show up to the party when quartz didn't get an invitation. Now, here's the golden rule, and I mean golden. Write this down. Quartz and feldspathoids are like cats and dogs. They don't hang out together. They're mutually exclusive. If you see quartz, you won't see nepheline. If you see nepheline, quartz is nowhere to be found. They rarely exist in equilibrium, kind of like your eccentric relatives at a family dinner. This is one of those beautiful geological certainties in a world of continuous variation. Ladies and gentlemen, welcome to the Mineral Popularity Contest. In this corner, we have the felsic minerals, also called leucocratic, which means light-colored in Greek. These are your quartz, orthoclase, plagioclase, and nepheline. They're light in color, low in density, and they're fashionably late to the crystallization party. Think of them as the lightweight champions. And here's a nerdy mnemonic to help you remember. Felsic comes from feldspar, feldspathoid, and silica. Get it? I know. Geologists are hilarious. In the opposite corner, we have the mafic minerals, melanocratic, meaning dark-colored. These bad boys are your micas like biotite, pyroxenes like augite, amphiboles like hornblende, and olivines. They're dark, they're dense, and they crystallize early. These minerals show up first to the party and stay late. Mafic stands for magnesium and ferric iron. These are the heavyweight minerals, literally. Here's the cool part. When magma cools, it's not random. The mafic minerals crystallize first because they are stable at high temperatures. The felsic minerals form later as things cool down. It's like a geological timeline frozen in stone. So next time you look at a rock, you're literally seeing a snapshot of the crystallization sequence. How cool is that? Picture this: magma beneath Earth's surface, trying to decide how it wants to grow up. Its career path depends entirely on where it ends up when it cools. Let me introduce you to the 3 geological neighborhoods. Volcanic rocks are the adrenaline junkies. They erupt onto Earth's surface, low pressure, rapid cooling, gas escaping everywhere like a shaken soda can. The result? Glassy or partially crystalline textures. The magma cools so fast that minerals barely have time to form proper crystals. It's like trying to bake a cake at 800 degrees. You're going to get some weird results. Hypabyssal rocks are the middle children. They form at intermediate depths in dikes and sills, those sheet-like intrusions that cut through existing rock. They get some time to cool, so they develop intermediate textures, often porphyritic, with those cool, big crystals suspended in finer ground mass. It's the Goldilocks zone of rock formation. Plutonic rocks are the patient ones. Deep underground, high pressure, slow cooling, volatiles retained. These rocks take their sweet time. We're talking thousands to millions of years of cooling. The result? Coarse, holocrystalline textures where every mineral gets to grow big, beautiful, interlocking crystals. It's like the difference between instant coffee and a slow-brewed artisan pour-over. Both are coffee, but the process matters. So remember, same magma composition, 3 different depths, 3 completely different rock textures. Location, location, location. It's not just for real estate. All right, everyone, this is it. The grand unification! This table is basically the periodic table of igneous rocks. If you understand this, you understand igneous petrology. Let me break down this beautiful matrix of geological destiny. Along the top, we have our chemical axis, oversaturated with quartz, saturated with just feldspars, and undersaturated with those feldspathoids we talked about. That's your what it's made of axis. Down the side, we have our depth axis, plutonic rocks formed deep, hypabyssal rocks in the middle zone, and volcanic rocks at the surface. That's your where it was born axis. Now here's where it gets fun. Moving vertically changes the chemistry. Same cooling history, different ingredients. Moving horizontally changes the cooling history. Same ingredients, different cooking time. It's like having the same cookie dough, but baking it at different temperatures. So granite porphyry, and rhyolite? Same chemical composition, just formed at different depths. Syenite porphyry, and trachyte? Also siblings, just from different neighborhoods. This table is your Rosetta Stone. Learn this, and you can name basically any igneous rock you'll encounter. It's literally that powerful. Frame it, memorize it, tattoo it on your arm if you have to. Okay, maybe don't do that last one, but you get the idea. Welcome to the celebrity rocks of the plutonic world. If igneous rocks had a Hollywood Walk of Fame, this series would own half the stars. Let's talk about the Granite Diorite series. These are your mountain builders, the oversaturated plutonic rocks that literally construct the foundations of continents. Granite is the superstar. It's got quartz, and here's the key. Orthoclase feldspar is greater than plagioclase. It's like the quarterback of the igneous rock team. Everybody knows it, everybody loves it. Granite countertops, granite monuments, granite mountains. This rock is everywhere. Granodiorite is granite's slightly less famous, but arguably more important sibling. Here, plagioclase increases and starts taking over. Fun fact, this is actually the most common rock in the Cordilleran mountain ranges. So while granite gets all the glory, granodiorite is out there doing the heavy lifting. It's the working-class hero of plutonic rocks. Diorite is where quartz becomes minimal, and plagioclase dominates over orthoclase. It's darker than granite, and compositionally it's getting closer to the basic end of the spectrum. The graph here shows you exactly how the mineral proportions shift. Watch quartz and orthoclase decrease while plagioclase marches upward. It's a continuous spectrum, but we've named the major landmarks. These rocks form when continental crust melts or when you have complex magma mixing events. They're the signature rocks of subduction zones and continental collisions. Basically, wherever tectonic plates are having a major disagreement. Time to meet the syenite family, the cool, alkaline cousins of granite. These rocks are dominated by alkali feldspars, and they've got some serious personality. Syenite itself is like granite's edgier sibling, Lots of alkali feldspar, but here's the twist. Little to no quartz. It's saturated, sitting right at that boundary. When silica drops even lower, we enter the undersaturated zone, and nepheline cyanide appears. Alkali feldspar plus nepheline, that felspathoid we discussed. Remember the golden rule? No quartz allowed here. Monzonite is the diplomat. It has equal amounts of plagioclase and alkali feldspar. It's transitional, trying to make everyone happy. Now, let me tell you about larvacite. This is that gorgeous rock with the shimmering blue crystals you see in that photo. In the commercial world, it's often mislabeled as blue granite, but geologists know better. It's actually an alkali syenite with this mineral called anorthoclase that produces that stunning bluish iridescence. It's from Norway, and it's absolutely beautiful. Next time you see countertops with that pearlescent blue shimmer, you can smugly correct the salesperson. Actually, that's larvacite, an alkali syenite. Watch their face. These rocks form in really interesting tectonic settings: continental rifts, alkaline complexes, places where magma has been enriched in sodium and potassium. They're relatively rare, which makes them extra special. Hold on to your rock hammers, folks, because we're descending into the dark side. Literally. Let's talk about gabbro and the ultramafic foundation, where rocks get dense, dark, and absolutely fascinating. Gabbro is the plutonic equivalent of basalt, calcium-rich plagioclase plus pyroxene, cooled slowly at depth. It's dark, it's coarse-grained, and it's the foundation of oceanic crust. While granite builds continents, gabbro builds ocean floors. Equal opportunity rock formation. But wait, there's more. Through this process called gravity differentiation, basically the heavy minerals literally sink because they're denser, you get this incredible stratification. Picture a layered cake, but made of minerals settling in a magma chamber. At the top, you get anorthosite, almost pure plagioclase, light-colored, low density, floating at the top like cream. It's the least dense, so it rises. At the bottom, you get peridotite, mostly olivine with some pyroxene. No feldspar at all. This is ultra-basic, and it's heavy, so it sinks. This is literally the stuff of Earth's mantle. And then there's dunite, that stunning bright green rock in the photo. It's pure olivine, or as close to pure as rocks get in nature. It looks like someone carved it out of green gemstone. This is what Earth's upper mantle is made of. These rocks are like geological archaeology. They reveal the internal processes happening deep in magma chambers. They show us how magma differentiates, how minerals separate by density, and how Earth's interior is structured. Pretty incredible for just rocks, right? Welcome to the middle world, the hypabyssal zone. These rocks form in dikes and sills, those sheet-like intrusions that cut through existing rock like geological sandwich fillings. They're the bridge between the deep plutonic realm and the surface volcanic world. Dolerite is the hypabyssal equivalent of gabbro. It's got this distinctive ophitic texture. That's where pyroxene crystals intergrow with plagioclase in this really cool interlocking pattern. If you look at it under a microscope, it's like a jigsaw puzzle where the pieces actually grew into each other. Nature's version of Tetris. This texture happens because the rock cooled at just the right rate. Fast enough that crystals interfered with each other's growth, but slow enough that they still formed visible crystals. Lampriphire is the drama queen of dike rocks. The name comes from Greek words meaning shining porphyry, and they're characterized by this texture called panidiomorphic. That's a fancy way of saying all the crystals are perfectly formed with beautiful faces. These are dark rocks, often with micas and amphiboles, and they frequently contain interesting, volatile, rich minerals. They're relatively rare and tend to show up in really specific geological settings. Porphyries in general are any rock with large phenocrysts floating in a finer ground mass, like chocolate chips in cookie dough, but geological. Granite porphyry, syenite porphyry, they all formed when some crystals grew slowly at depth. Then the remaining magma moved up and cooled faster, creating that two-stage texture. These hypabyssal rocks are like time capsules of magma transport. They show us the plumbing system of volcanic regions. Let's hit the surface and meet the volcanic equivalents of our plutonic celebrities. Say hello to rhyolite and dacite, the acidic lavas that are basically granite's hyperactive cousins. Rhyolite is what happens when granite composition magma erupts onto Earth's surface. Rapid cooling literally freezes the flow in motion, creating these beautiful flow bands. You can actually see the swirls and layers where the lava was moving. It's like a geological lava lamp frozen in time. Sometimes you can even see the direction the lava was flowing. How cool is that? Now check out obsidian in that photo, the volcanic glass that's so perfectly black and shiny. This is the extreme version. The magma cooled so fast that crystals didn't have time to form at all. Zero crystallization. It just instantly solidified into glass. Ancient civilizations used obsidian for tools and weapons because it fractures into incredibly sharp edges. Sharper than modern surgical steel, actually. It's volcanic, but it's also practical. Dacite is the volcanic equivalent of granodiorite. It's named after Dacia, the Roman name for an area in Hungary where it was first described. It's slightly less silica-rich than rhyolite, with more plagioclase and some dark minerals giving it a gray color instead of that pink or light color you see in rhyolite. These rocks are associated with explosive volcanism. Think Mount St. Helens, not Hawaiian lava flows. The high silica content makes the magma viscous, sticky, and prone to violent eruptions. So when you see rhyolite or dacite, you're looking at evidence of Earth's more dramatic moments. Time to meet the volcanic rocks with the coolest names in geology. Seriously, whoever named these rocks had a sense of style. Trachyte, the name literally means rough in Greek, and it's called that because it feels rough to the touch. It's the volcanic equivalent of syenite, dominated by alkali feldspars. But here's what makes it special. Trachytic texture. Look at that diagram. The alkali feldspar crystals are flow-aligned, all oriented in the same direction like they're combing their hair. This happens because the lava was flowing as the crystals were forming, and they literally got pushed into alignment by the flow. It's like geological streamlining. Phonolite might have the best name in all of petrology. It comes from Greek words meaning sound and stone. Why? Because when you strike a thin slab of phonolite, it rings like a bell. Seriously, it makes a clear, musical clinking sound. Hence the alternative name, clinkstone. Imagine being the geologist who first discovered this. Hey everyone, this rock is musical. Phonolite is the volcanic equivalent of nepheline syenite, which means it's undersaturated. You'll find nepheline or lucite in there, but never quartz. Remember our golden rule. These rocks are associated with continental rift zones and alkaline volcanic provinces. They're relatively rare, which makes finding them extra exciting. Both trachyte and phonolite represent magmas that were enriched in alkalis, sodium and potassium, and relatively low in silica. They're the result of really specific magmatic processes, which makes them geologically significant indicators of what was happening in the mantle and crust when they formed. And now, ladies and gentlemen, the heavyweight champions of volcanic rocks. If volcanic rocks had a popularity contest, andesite and basalt would be fighting for first place. Together, they make up the vast majority of volcanic rocks on Earth's surface. Andesite is named after the Andes Mountains in South America, where it's spectacularly abundant. It's classified as do-felsic, meaning it's got more than 5/8 felsic minerals. That's about 65% felsic, 35% mafic, as you can see in the bar chart. It's dominated by plagioclase, with some dark minerals like hornblende or pyroxene. Andesite is the signature rock of subduction zones, those places where oceanic crust dives beneath continental crust, melts partially, and produces this intermediate composition magma. It's the volcanic equivalent of diorite, and it's the rock of mountain-building episodes. Ring of Fire, Andes, Cascades, all andesite country. Basalt is basically the default setting for volcanic rocks. It's mafelsic, equal proportions of felsic and mafic minerals, about 50-50. The composition is calcium-rich plagioclase, especially labradorite, plus augite, a pyroxene. Basalt is associated with oceanic islands, mid-ocean ridges, and hotspot volcanism. Think Hawaii, Iceland, the ocean floor, all basalt. It's the most abundant volcanic rock on Earth, and probably in the solar system. Mars is covered in it. The moon's dark patches? Basalt. It's literally the universal volcanic rock. Here's a bonus rock. Spilite is a sodium-rich variety of basalt that forms underwater and creates these distinctive pillow structures, those bulbous, pillow-shaped masses that form when lava erupts into water and instantly chills. If you see pillow structures, you're looking at ancient seafloor. These two rocks, andesite and basalt, tell us about plate tectonics, mantle composition, and volcanic processes. They're everywhere, and for good reason. They represent the most common ways Earth creates volcanic rocks. All right, class, let's bring it all home. Look at this beautiful cycle of differentiation. This is the big picture, the master narrative of igneous petrology. Classification isn't just an exercise in memorization, or an excuse to make overcomplicated tables that give you nightmares. No, classification is a tool for understanding origin. Every rock name is like a coordinate on a geological map. It tells you exactly where that rock sits in terms of its composition and its occurrence. Think about what we've learned. A rock's identity comes from what it's made of, its chemical and mineral composition, and where it was born, its cooling history and tectonic setting. Those two factors, composition and occurrence, define everything. The cycle goes like this. Magma forms from melting in the mantle or crust. The cooling environment determines texture. Fast cooling gives volcanic. Slow gives plutonic. Mineral separation through crystallization and differentiation creates the chemical diversity. And finally, we get our final rock type, whether it's granite or basalt or anything in between. But here's the beautiful part. By understanding this cycle, we're not just naming rocks, we're reading Earth's biography. Every rock tells a story about where it came from, what happened to it, and what that means for Earth's processes. That's the power of classification. So next time someone asks you why you're learning all these rock names, tell them this: I'm not just memorizing names, I'm learning to read the language Earth uses to tell its story. And that, my friends, is what makes petrology absolutely awesome. Thanks for joining me on this geological journey. Now get out there and start identifying some rocks. Class dismissed.